Welcome to Geology 108, the rock cycle. Once Earth was equipped with the oceanic and continental crusts during the Hadean, the primitive water cycle started with continuous evaporation from the ocean's surface, transport of water vapor in the atmosphere, precipitation and land masses, with stream and river transport back to the oceans. Erosion from the constant attack of precipitation and wave action, coupled to rapid circulation of rocks between the crust and the upper mantle, ignited the rock cycle. In the Hadean period, after magma cooling created the basaltic oceanic crust and the granitic continental crust, the rock cycle formed new types of rocks and minerals across planet Earth. A rock is any naturally formed, non-living, coherent aggregate mass of solid matter that constitutes part of a planet, asteroid, moon, or other planetary object. Minerals are the most common and abundant building blocks of rocks. Minerals are non-organic, naturally occurring, with a definite chemical composition, solid materials. Natural minerals are never pure, with impurities often giving them an interesting luster. Many rocks are dominated by one or more minerals. For example, peridotite is made of mostly pyroxene and olivine. Granite is made of quartz, feldspars, and pyroxene or mica. Everything we know about Earth ultimately comes from the testimony of the rocks and minerals. All across the globe are three basic kinds of rocks: igneous, sedimentary, and metamorphic, that collectively make up Earth's great cycle of rock formation. The first solid rocks at Earth's surface were examples of igneous rocks, rocks that form from the hot, molten state. Basalt is an igneous rock, as is peridotite and granite. Igneous rocks come in two principal types: volcanic rocks, also called extrusive rocks, form quickly at Earth's surface as magma or lava solidifies in air or underwater. The second major type of igneous rocks harden underground, typically form larger grains and are called intrusive or plutonic rocks. Earth's first crust was composed almost entirely of igneous rocks, but sedimentary rocks, the second of the three major groups, account for 2/3 of all rocks exposed on Earth's surface today. They form wherever fragments of other rocks accumulate into layers. Many sedimentary rocks form from tiny particles or sediments, but may also form directly by chemical precipitation from water. One familiar example may be salt deposits from a dried up lake. There are places where immense layers of salt have accumulated. Some of those have been mined for centuries for table salt. In addition, many other chemicals can form rocks by precipitation. The most common of these is limestone, which forms from calcium carbonate. The rich variety of metamorphic rocks encompasses the third great group of rocks on Earth. As igneous or sedimentary rocks are slowly buried deep, they are subjected to intense heat and pressure and they can transform into new kinds of rocks. Igneous, sedimentary, and metamorphic rocks all participate in the rock cycle. Igneous rocks, once formed, can be weathered to eventually form sedimentary rocks. Or they can undergo metamorphism, that is, an alteration of their composition or structure by heat, pressure, or other natural cause. In such a way, layers of sedimentary rocks can be transformed into metamorphic rocks. All three kinds of rocks can be partially melted and reformed as new igneous rocks. New igneous rocks formed by cooling of magma and lava, involving a change of state from liquid to solid. In this way, the cycle closes and can go on perpetually. The rock cycle does not only involve the surface layers. Rocks from the mantle also go through this cycle, albeit more slowly. In 4.5 billion years, rocks may have voyaged from the bottom of the lower mantle to the Earth's surface and back, perhaps 5 times. Exposed rocks are weathered, creating a local regolith, that is, a layer of unconsolidated rocky material covering bedrock. Weathered material is then brushed away and transported as sediment. Then burial and lithification of sediment creates sedimentary rocks. As tectonic forces recycle large slabs of rocks into the mantle and create deep troughs and high mountains, sediment sources and sinks are formed. Material that is uplifted to great height or buried at great depth is subjected to different conditions of pressure and temperature and fluid content. With tectonic activity, such as mountain building or rifting, heat, pressure, and stress alter the texture and mineral assemblage of existing rocks in a process called metamorphism. In this way, the rock cycle never ceases. All of Earth's atoms are recycled. The atoms are always shifting around, creating bonds with different companions, but it is always the same matter recycling over and over. Time is another crucial aspect of understanding the rock cycle. It often takes immense spans of time, hundreds of millions of years, to make new rocks and transform them. Consider an outcrop that reveals many different layers of rocks, like the Grand Canyon in Arizona, or Bryce Canyon in Utah. These spectacular landscapes reveal a myriad of horizontal layers of sedimentary rocks with different texture and composition, indicating that they formed under different climates or different water depth. How could such a sequence have occurred, and how long did it take? Another geological site of historical importance is Siccar Point, Scotland, discovered and interpreted by James Hutton in 1788. At Siccar Point, gently sloping strata of 370 million year old sandstone a sedimentary rock formed in a desert environment, overlie near vertical layers of 435 million year old gray rock, another type of sandstone containing marine fossils, separated by a sharp angular unconformity. An angular unconformity is a buried erosional or non-depositional surface separating two rock masses or strata of different ages, indicating that sediment deposition was not continuous. The top and bottom layers at Siccar Point are separated by a gap of 65 million years, during which erosion was taking place. James Hutton used Siccar Point to demonstrate the cycle of deposition, folding, erosion, and further deposition that the unconformity represents. He understood that such unconformities provide evidence for the enormity of geological time and the antiquity of planet Earth. The conclusions of James Hutton relied on the principle of uniformity, or uniformitarianism. Principle of uniformity is central in geology and represents the assumption that the same natural laws and processes that operate in our present-day scientific observations have always operated during Earth's history. This does not imply that all changes have been gradual. For example, collisions with giant meteorites have had an immediate global impact on Earth. Earth's history is considered to have been a slow, gradual process punctuated by occasional natural catastrophic events. Earthquakes, floods, fires, or other extremely rapid processes in view of geological timescales that quickly and profoundly affect the environment. The processes of sedimentation, burial, uplift, tectonic forces, and more are acting in the present, albeit very slowly. For the same geological forces to shape vertiginous landscapes like the Grand Canyon, Bryce Canyon, or the Siccar Point Formation, it must take an almost unimaginably long time. Each step of the formation process must have taken tens to hundreds of millions of years. Thanks to Hutton and his successor geologists, we now know that Earth's age is more than 4.5 billion years. And the existence of structures like the one at Siccar Point becomes comprehensible. Hutton had captured a crucial feature of what we call the rock cycle, where surface rocks are ceaselessly broken down and become the raw materials for the creation of new rocks. Igneous rocks are the first rocks ever made on the planet, by gradual cooling of hot magma. Yet, there are many types of igneous rocks based on their composition and texture. When magma or lava solidifies, the mineral assemblage is the same for both intrusive and extrusive rocks. However, the texture is different. Volcanic or extrusive rocks experience rapid cooling and have a fine-grained texture. Lava cools so rapidly that minerals do not have time to grow large. Some lava cools so rapidly that it forms glass, for example, obsidian. Plutonic or intrusive rocks tend to be coarse-grained because magma within the crust cools slowly and has the time to grow crystals. An extremely coarse-grained rock is called pegmatite. A mixture of large and small grains is called porphyry. Extrusive and intrusive rocks share the same composition. Rocks that contain a lot of silica are called felsic, and rocks that contain little silica are called mafic. Felsic magmas have a higher viscosity than mafic magmas and tend to produce explosive volcanism. In contrast, mafic magmas and lavas produce effusive volcanism, which is the most common on Earth. Felsic and mafic rocks can be easily recognized. Felsic magmas contain lighter colored minerals, such as quartz and autoclase feldspar. Mafic rocks are rich in magnesium and iron and are often dark in color. The texture of igneous rocks also depends on whether they are intrusive or extrusive. Intrusive rocks of increasing silica content are peridotite, gabbro, diorite, and granite. They are referred to as ultramafic, mafic, intermediate, and felsic, respectively. Extrusive rocks of increasing silica content are called comotite, basalt, andesite, and rhyolite, also referred to as ultramafic, mafic, intermediate, and felsic, respectively. Rocks from the mantle and the oceanic crust are predominantly mafic. Rocks forming the continental crust are lighter and predominantly felsic. On early Earth, when the first rains began to fall on the first igneous rocks, small mineral grains were washed off from those recently hardened igneous rocks, basalt and granite. When rock is exposed at Earth's surface, it is susceptible to alteration by the action of water, wind, and other agents that may act to alter the chemical composition of the minerals present or to break the rock apart. Given sufficient time, the result is conspicuous decomposition and disintegration of the rock by processes known collectively as weathering. The product of rock weathering is a layer of broken up, disintegrated rock matter called regolith. Regolith embodies the entire unconsolidated cover that overlies coherent bedrock. It has been formed by weathering, erosion, transport, and/or deposition of older material. Essentially, everything between fresh rock and fresh air. Regolith is present on Earth, but also on the Moon, Mars, some asteroids, and other terrestrial planets and moons in the solar system. The unconsolidated loose rock and mineral particles that constitute the regolith are collectively referred to as sediment. When sediment is picked up by wind, water, or ice, transported to another location and deposited, it is called alluvium. There are two important families of sediment. The principal difference between them is the way that sediment was transported. Clastic sediment is simply bits of broken rock and minerals that are moved as solid particles tend to be the rock-forming minerals, such as quartz and feldspar, that are most durable during weathering. Chemical sediment is dissolved material that is transported in the form of a solution. It is deposited when the dissolved minerals are precipitated. Alluvial and aeolian deposits differ in grain size and can betray their transport mechanism, streams and wind, respectively. Alluvial sediments are deposited by rivers and consist of clasts of varying grain size: silt, sand, clay, and gravel, as well as much organic matter. Most of the dust carried by dust storms is in the form of silt-sized particles. Deposits of this wind-blown silt are known as loess. Over time, thick layers of sediment accumulated, especially in big fan-like deltas at the mouth of rivers. These sediment layers can reach incredible thicknesses. In many places on Earth, sediments are several kilometers deep. For example, the campus of the University of Southern California is sitting on top of 3.5 kilometers of marine sediments that accumulated when the Los Angeles basin was submarine a few million years ago. The basin, filled with organic matter that slowly turned into large oil and gas reservoirs, an example of low temperature metamorphism or diagenesis. Weathering breaks rocks into smaller particles, and nature continuously sweeps these particles away. This sediment transport is called erosion. The chief medium of erosion is flowing water in the form of liquid or ice. And the driving force is gravity, as any mass seeks to reduce its gravitational potential. Wind is also an important medium of erosion. After transport through streams and rivers or through wind, sediment is laid down into layers in shallow lakes and on the ocean floor, called sedimentary sinks. Sedimentary sinks are low-lying areas largely controlled by plate tectonics. For example, trough, rift valleys, trenches, and accretionary wedges and basins are formed along the way with the formation of new oceanic crusts and when the continents are reshaped. Sediments can accumulate in deep basins many kilometers deep. The interactions of tectonic plates provide a regional setting for the distribution of sources and sinks. Spreading centers and mid-ocean ridges where new oceanic crust material is being formed. The surrounding abyssal plains constitute the world's widest sedimentary sinks. At collisions, continental collisions, where two granitic slabs collide, the colossal lateral forces deform the crust, forming mountains, a process called orogeny. Orogenic highs provide a sedimentary source. The large wedge of sediments along the boundary is a sedimentary sink. Intense volcanism occurs at subduction zones, where the oceanic crust is recycled into the mantle. This creates neighboring sedimentary sources and sinks as well. Sediments start as loosely consolidated grains, just like sand at the beach. But when sediments are buried deep, the temperature and pressure increases and hot water flows through the sand and silt layers, dissolving and redepositing glue-like chemicals. All that pressure, heat, and the effect of mineral-laden water weld the bits of sediments together into new layered rocks. The process by which sediment or regolith becomes rock is called lithification. From sediments, this produces a sedimentary rock. Bedding is a banded appearance in many sedimentary rocks that results from sediment deposition in layers. The process of lithification has multiple steps. As sediment accumulates, the pile grows thicker and causes compaction. For the particles to adhere to each other, either cementation or recrystallization must take place. These low temperature and low pressure changes that happen to sediment after deposition are collectively called diagenesis. The end result of lithification is a sedimentary rock, which can reveal information about the source region and the weathering and deposition process that formed it. Besides bedding, the presence of fossil is an important indicator of sedimentary origin. The rich variety of metamorphic rocks encompasses the third great group of rocks on Earth. As igneous or sedimentary rocks are slowly buried deep, they are subjected to intense heat and pressure, and they can transform into new kinds of rock. Metamorphism also produces new mineral assemblages that are stable at the new pressure and temperature conditions. Rocks can be heated and stressed by burial, exposure to igneous intrusions, or collision. Stress refers to the forces acting on a material. When all forces are equal in all directions, it is called pressure. Differential stress is a stress that is not equal in all directions. The term stress implies direction and is a more useful term than pressure, especially since metamorphic rocks record differential stress in their textures. Stress produces the parallel alignment of certain minerals that give the rock a stripy pattern, like in gneiss, or foliation, where layers form parallel to the direction of shear. Different kinds of metamorphism reflect the importance of mechanical deformation or chemical recrystallization. The lowest degree of metamorphism, called diagenesis, is involved in the lithification of sedimentary rocks like shale that forms from the compaction of mud. Low-grade metamorphism takes place at temperatures between about 200 and 320 degrees Celsius and relatively low pressure. Low-grade metamorphic rocks are generally characterized by an abundance of hydrous minerals, for example, slate. Medium-grade metamorphism takes place at approximately 320 to 450 degrees Celsius and at moderate pressures. Low-grade hydrous minerals are replaced by micas such as biotite and muscovite, and non-hydrous minerals like garnet may grow. At even higher temperature, schists or gneiss is formed, with minerals such as garnet starting to appear. Over the rock cycle, rocks change composition, texture, creating even new minerals. Its constant renewal, driven by a combination of plate tectonics, weathering, sediment transport, and deposition, is responsible for the great variety of landscape on the planet.